So here we are, the last lecture, Intro to Organic Chemistry. So the way this story begins has to do with reactions, trends, and observations that were obtained, all the way dating back to the 1700s. In fact, a lot of the work done by alchemists kind of led on to the realm of organic chemistry too. And at the time, in the 17th century, um, Berzelius was one of the proponents that organic chemistry was the chemistry of molecules only produced and found in living organisms. And this idea known as vitalism, went on for, a good 100 years or so. And Berzelius, by the way, wasn't just any old dummy. He actually contributed quite a bit to the field of chemistry. He, along with Humphrey Davy, was able to isolate and identify strontium and barium as elements in the periodic table. He also was able to isolate and identify silicon as a new element. And so he was a heavy duty, member of the chemistry community back then. And even with the help of GAN, he also discovered selenium. So he contributed quite a bit to the field of chemistry. So he was a top dog. So you can't really say it's like, oh well, that was dumb of him to say that this was just a field that could be found in only living organisms. That's technically true to some extent. But then comes a student of his, Friedrich Wohler. And this particular student, what he does is he carries out a reaction between silver uh, isocyanate and ammonium chloride. And pretty much he mixes these two things, which are inorganic components. He makes ammonium cyanate out of them, and of course he precipitates silver chloride, which he removes by filtration. But the ammonium cyanate then is heated, and upon heating the inorganic component, you actually undergo a reaction, a rearrangement, which leads to formation of the organic fragment known as urea. And this was basically the beginning that showed that, yeah, vitalism is not true. You could make organic molecules even from inorganic molecules themselves, and definitely outside of living organisms. So vitalism kind of went down the toilet after that. And nowadays, organic chemistry, simply put, is the chemistry of carbon. Not every carbon molecule out there will be considered organic, but the vast majority of them are. And the chemistry revolves around this element when it comes down to organic chemistry. One thing I kind of want to show you is the electronegativity table. In respect to carbon, we have a value of 2.55, and in respect to that value, you will notice that all the elements to the right, nitrogen, oxygen, fluorine, are more electronegative. All the halogens are pretty much more electronegative than carbon. Sulfur, to some extent, you can see that iodine and sulfur are a little bit, on the close side to call them fully um, polar bonds, but they are more electronegative. Hydrogen, on the other hand, is less electronegative than carbon. So that's just kind of something to keep in mind, which kind of helps out ultimately making sense of the chemistry of organic molecules. Okay, now let's talk about the index of hydrogen deficiency, because what we're going to do in this lecture, there's no way we can cover every single aspect of organic chemistry. The field is just way too vast and too large. The class alone takes a full year for you to get the full grasp of it. And that's just at the introductory level, right? After that, you have to take advanced classes. So we're going to only focus on specific subtopics. The first one is known as the Index of Hydrogen Deficiency, IHD. Alright, so the Index of Hydrogen Deficiency tells you how unsaturated a molecule is. And to be most exact, we are comparing this to a level of saturation based on the amount of carbon that your molecule has. Specifically, based on this equation, your molecule is saturated if you have twice the number of hydrogens as you do carbons plus 2 more. This particular formula is one that we're gonna observe for molecules known as alkanes. But if you have this many hydrogens compared to your number of carbons, that's what N stands for, then you have a saturated hydrocarbon. Now from this, we're going to subtract what we call the equivalent hydrogens, and I'll show you in a second what that means, which then it's all divided by 2. This tells you the index of hydrogen deficiency, which itself will tell you something about the structure of the molecule. Alright, so as I was saying, this is the alkane formula, and I'll describe that in more detail in the next video. But for now, what you need to know is that this tells you that the compound is saturated if you actually attain that number of hydrogens. Now, the equivalent hydrogens, here's what you have to be a little bit careful, because if your actual formula contains hydrogen, well, you count every hydrogen that there is. But if it also contains halogens like chlorine, fluorine, bromine, you're going to count the halogens as if they were hydrogens. Oxygens and sulfurs you completely ignore, so almost as if they weren't there in terms of the hydrogen count. But nitrogens and phosphorus atoms, for every one of those atoms you have, you're going to subtract 1 H. And when you basically apply all of those changes, you end up with your equivalent number of hydrogens. Okay, so let me give you pretty much an example, well, a few examples of how this actually pans out. So let's say we have the molecule C4H10. Applying the formula, we have 4 carbons. If we input the number of 4 for N, we'll have 2 times 4, which is 8, plus 2, which is 10. Now, in the molecule itself, we have 10 hydrogens, so that's the number of equivalent hydrogens. We have 10 minus 10, which is 0. All divided by 2 is still 0. Now, what this tells you, having a value of 0 for the IHD, what it tells you is that the molecule is saturated. You have the maximum number of hydrogens present on it. But let's see now what happens when we change the structure a little bit. Okay, so let's take a look at these cyclic structures, right? So we have a square ring right here, and over here we have a triangular ring. Both of them have the same formula, C4H8. If we apply the formula for the IHD, well, we have 4 still for carbon, so we have 2 times 4, which is 8, plus 2, which is 10. And we only have 8 hydrogens here, so we have 10 minus 8, which is 2. 2 divided by 2 tells you that the IHD is 1. And simply by making the change of having a linear hydrocarbon to a cyclic one, now we have increased the IHD by 1 value. And what this tells us is that you have a deficiency of hydrogen. Instead of having the full maximum amount, which would have been 10 for 4 carbons, now you have 2 less. So that's what the IHD is telling you. But ultimately, we're going to correlate this number to the idea of having maybe a cyclic ring in the structure. And I do say maybe because it turns out that when you look at hydrocarbons where there's a double bond, the formula is also deficient on hydrogen. You have pretty much the same formula as that of the cyclic compounds. And so you end up with the same IHD of 1 if you have only a single, if you have only a double bond present in there. So what this means is that if you have an IHD of 0, there's going to be no multiple bonds and there's going to be no rings in the structure. That's what the IHD is ultimately telling you. If you have an IHD of 1, you will have either a double bond or a ring. And let's say you have a triple bond. Well, what happens with a triple bond? If you count the number of H's for these 4 carbons, 1, 2, 3, and 4, you only have 6 hydrogens in there. And if you apply the formula, 10 minus 6 divided by 2, you end up with an IHD of 2. So the IHD keeps going up. Oh, and by the way, this is additive. If you have 2 rings, that will count for an IHD of 2. If you have 2 double bonds, that will count for an IHD of 2. If you have a triple bond, that counts as an IHD of 2. So the possibilities kind of increase in value. And here I'm kind of showing you all of that, right? So you could have a triple bond, or you could have 2 double bonds, or you could have 2 rings, or you could have a double bond and a ring. And all of those possibilities will give you the same value for the IHD. Now, the last one that I want to mention is when you have IHD values of 4 or more. The possibilities are pretty huge for that. But usually, we are talking about having a benzene ring present. And we're going to talk about what that means ultimately in the next video. But be on the lookout for values of 4 or greater for the IHD, because that will tell you, yeah, possibly you have a benzene. It's not guaranteed that you'll have benzene, but it is a possibility. Alright, so I'm going to show you examples of isomers on the next video. But for now, let's stop right here and let's reconvene next.